Hey everyone, and welcome. So, if you've ever felt like math is some kind of secret language that you're just not in on, then you are in exactly the right place. Today, we're going to decode the toolkit that secretly runs, well, pretty much everything, from the lottery to the stock market. Let's unlock your new superpower.
No, seriously, think about it for a second. What if you knew with 100% certainty what was going to happen next?
I mean, you could pick the winning lottery numbers every single time.
Or you'd know exactly which questions were going to be on your next big test, right? No more studying Chapter 7 only to get tested on Chapter 2.
You'd know exactly which card was coming next at the poker table. Now, look, while we can't actually see the future, there is a mathematical toolkit that gets us incredibly close. And the first step to becoming a master of prediction, it's a lot simpler than you think. It all starts with just counting.
So, welcome to level 1 of your new superpower. See, before you can figure out the chance of something happening, you have to know every single way it could happen. And for that, we need our first tool.
Meet the factorial. It's written with an exclamation point, and honestly, that's because the results are so ridiculously huge they make you want to shout. You just take a number and multiply it by every whole number smaller than it, all the way down to 1.
And this is where things get wild. Let's say you have just 5 different books. The number of ways you can arrange them on a shelf is 5 factorial. That's 5 times 4 times 3 times 2 times 1, which is 120 different arrangements from just 5 books.
Okay, now let's scale that up. The number of ways you can shuffle a standard 52-card deck is 52 factorial. That number is so big it has 68 digits. It's so massive that it is statistically almost certain that no 2 shuffled decks of cards have ever been in the same order in the entire history of the universe. Seriously, that's just mind-blowing.
Okay, so we can count every possibility, even when the numbers get totally astronomical. But what if we don't care about all of them? To figure that out, we have to level up and ask the single most important question in this entire field. Does the order matter?
This one simple question splits our whole toolkit right in two. If the order is absolutely crucial, like, who gets gold, silver, and bronze in a race, we're talking about permutations. But if the order is totally irrelevant, like just throwing toppings on a pizza, then we're dealing with combinations.
Right, so with permutations, sequence is everything. Imagine 8 runners in a race, and we want to know how many ways the top 4 can finish. Coming in first is completely different from coming in fourth, right? That specific ranking creates a unique outcome. And it turns out there are a whopping 1,680 unique ways for those runners to finish in the top 4.
But with combinations, we just toss order right out the window. I mean, pepperoni, then olives, then pineapple is the exact same pizza as pineapple, then olives, then pepperoni. Who cares how they got there as long as they're on the pizza? Because of this, the number of outcomes just plummets. If we pick 5 toppings from 7 choices, there are only 21 unique pizzas we can make. See that massive drop? From 1,680 down to 21? That's the power of knowing when order just doesn't matter.
All right, level 3. We've totally mastered counting all the possibilities. So now, let's level up and figure out the actual chance of any one of those possibilities happening. We're shifting from how many to what's the chance.
And you know what? The basic formula is beautifully simple. Theoretical probability is just the number of ways your thing can happen divided by the total number of things that could possibly happen. Your answer is always going to be a number between 0, meaning it's impossible, and 1, meaning it's a sure thing. But to calculate that, you got to know if your events are independent or dependent. Independent events, they just don't care about each other. Think rolling a die and flipping a coin. But dependent events, well, they're a little more needy. What happens first directly messes with what can happen next.
And this is where it gets really, really cool. Let's say you want to draw 2 aces from a deck. The chance of drawing that first ace? It's 4 out of 52. But once you pull that ace out and hold it in your hand, you've changed the game. Now there are only 3 aces left and only 51 total cards in the deck. The first event completely altered the probability of the second. It's like the deck has a memory.
Okay, time for level 4, and this is where things get messy. So far, we've been living in this perfect world of math, right? Where a coin has a perfect 50-50 chance of landing on heads. But what happens when we take that beautiful, clean math into the unpredictable, messy real world?
Well, we get something called empirical probability. This thing ignores all the theory and is based only on what you actually see happen in an experiment. You roll a die, you flip a coin, you survey some people, and you just write down what happened. No assumptions, just data.
So in a perfect mathematical world, a fair die should give you a 50% chance of rolling an even number and a 50% chance of rolling an odd one. It's perfectly balanced, clean, and totally predictable.
But check out what happened when someone actually rolled a die just 30 times. The number 4 came up over a third of the time, and the number 6 barely showed up at all. You might start to think this die has a favorite number or something. This is the messy, weird reality you get with small experiments.
So, how do we fix this? Well, with something called the law of large numbers. This is basically the bridge that connects that messy reality back to our pure math. It says that the more times you repeat an experiment, we're talking thousands, even millions of times, your real-world results will get closer and closer and closer to the theoretical prediction. In the long run, the house and the math always wins.
And that brings us to our final level up. Since we know the math always wins in the long run, how can we use it to actually predict those long-term outcomes? This is exactly what casinos, insurance companies, and Wall Street traders do every single day.
They use something called expected value. You can think of it as the long-term average you should expect if you do something over and over and over again. For a 6-sided die, the expected value is 3.5. Now, obviously, you can never roll a 3.5, but if you rolled it 1,000,000 times and averaged all your results, your answer would get incredibly close to it. It's kind of like this. The expected value of your diet might be a salad, but the empirical value, well, that's often pizza, right?
And there you have it, your toolkit. From simple counting all the way to predicting long-term outcomes. You now have the power to see the difference between what should happen and what actually does. Which leaves us with one final, really important question to think about. How many times do you need to see something happen before you would trust the math enough to bet your life on it?